Welcome. Please turn to section 3.3 of your guided notes. This lecture is covering power functions and polynomial functions. By the end of the lesson, you'll be expected to identify power and polynomial functions, their degree, leading coefficient, and the end behavior of their graphs. A power function is a function that can be represented in the form f of x equals k x to the p power. This is where k and p are real numbers and k is known as the coefficient. Let's discuss the end behavior of power graphs. This table is taken from page 226 of the required textbook. So let's look at the cases of even powers versus odd powers. So if we have even power, you'll notice that the graph has ends that point in the same direction, either both up or both down. They both point up if our constant k is greater than 0, and recall these are of the form f of x equals k x to the p power. So if this k is greater than 0, it points up. If we have an even power and this k is less than 0, our graph will point downward. This means as we approach infinity on the positive x-axis, the graph will approach positive infinity. So that is right here. As x approaches positive infinity, f of x approaches positive infinity. As x goes towards negative infinity, our graph will approach positive infinity. Here, it's the opposite. As we approach positive infinity on the x-axis, we approach negative infinity on the y-axis. And as we approach negative infinity along the horizontal axis here, we approach negative infinity along the y-axis. So it looks like this is a typo. Please correct that. Next, let's look at odd powers. If the power here is odd, the ends of your graph will point in the opposite directions. If you have a positive constant, as you approach positive infinity along the horizontal axis, you should be approaching positive infinity along the y-axis. So that is another typo. I'm a bit surprised there are so many typos, but that's okay. We can just fix them, so please remove the negative sign here. Next, as we approach negative infinity, our graph will approach negative infinity as well. Now let's see if we can get through this last one without finding another book typo. As we approach positive infinity along the horizontal axis, we should be approaching negative infinity along the vertical axis. As we approach negative infinity along the horizontal axis, we should be approaching positive infinity along the vertical axis. That's here. So these are some typos on page 226 of the required textbook. If you have it in front of you as a printed copy, I would make these corrections. If you're looking at the digital copy available online on Canvas, you can go ahead and make these edits on your PDF editor. Let's look at example 1. Example 1, describing the end behavior of a power function. Describe the end behavior of the graphs of the functions given below. So we have f of x equals negative x to the 5th. Let's rewrite this as negative 1 times x to the 5th. This makes it very obvious what the value of k is. K equals negative 1. That is less than 0. So k is less than 0. And we have an odd power. This tells me as x approaches positive infinity, my graph should be approaching negative infinity. So it'll look something like this. And that would be in the bottom right of the boxes below. So as x approaches positive infinity, f of x will approach negative infinity. Also, as x approaches negative infinity, f of x should approach positive infinity. Let's look at the next example. F of x equals x to the fourth. I can rewrite this as 1 times x to the fourth. This tells me that k equals 1, so k is greater than 0. Our graph will look something like this. So as x approaches positive infinity, f of x will approach positive infinity. If you're looking at the cases from your book above, this would be even power positive constant. It is the one of 4 cases that we did not find a typo in. And as x approaches negative infinity, f of x will also approach positive infinity. Polynomial functions. Given a non-negative integer n, a polynomial function is a function that can be written in this form. And technically, you can have an x to the 0 power here, but if you remember, x to the 0 equals 1, so we can just leave that off. Also, this power of 1 you can leave off. We tend to not write numbers with an exponent of 1, because we could always write a number with an exponent of 1 in that case. So what are we looking at here? Each AI is a coefficient, so these are coefficients. This one cannot be 0. If it's 0, then this would be our degree, and the definition would get a little cloudy. But a sub n cannot equal to 0. The degree is the value on the power of the leading coefficient. This is the leading coefficient. And this n here is the degree of the polynomial. Each of these products is called a term of our polynomial. Let's look at example 2. Identify and describe the end behavior of the following polynomial functions. Also identify the degree and the leading coefficient. So what is our degree? This one is fairly straightforward. If you notice, I have a 5, x to the 4th, x squared, then no x. So it's really clear that this is the leading coefficient. So the leading coefficient is 2. The degree is 5. Since the degree is 5 and this leading coefficient is 2, this is like our k. So this tells me that k equals 2 and is greater than 0. So our graph is going to look something like this. There's going to be a lot of other stuff happening in between, but this is a really rough sketch. This tells me that as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. Let's look at the next example. F of x equals 5x squared times x minus 3 times x plus 2. So the degree is found with the leading coefficient, and if you notice, that will happen by multiplying 5x squared times x times x again. So the first term of this polynomial is going to be 5x squared times x, or 5x to the fourth. If you don't believe me, please pause the video right here and multiply this out manually. And actually, if you think you're not going to see this on an exam and get stuck, then please pause the video, multiply this out on scratch paper. This is simply a shortcut for finding the leading coefficient and the degree. The leading coefficient is 5. The degree is 4. Now, since the leading coefficient is 5, we say k equals 5, which is greater than 0, and our degree is even, so our graph will look something like this. There's going to be a whole other mess of stuff going on here, but in general, it's going to end up pointing upward despite whatever mess happens here in the middle. So as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x should also approach positive infinity. Next, let's look at intercepts and turning points of polynomial functions. A turning point of a graph is a point at which the graph changes direction. From increasing to decreasing. A polynomial of degree n will have at most n minus 1 turning points. The x-intercepts are the points at which the output values, that is the y values, are 0. The y-intercept is the point at which the input value, that is the x value, is 0. And the wording of this should give you a big clue as to how many we have of each. This is similar to a parabola, especially since a parabola is just a type of polynomial. So polynomials have exactly one y-intercept, but may have up to n x-intercepts. So let's look at example 3. Example 3. Drawing conclusions about polynomial functions given f of x equals 3x times x minus 2 times x plus 1. Determine the local behavior. And what does that mean? Your x and y intercepts, along with the degree and the number of turning points. So let's start with our x-intercepts. We let this equal 0, our y, which is our f of x. So we have 0 equals 3x times x minus 2 times x plus 1. This is factored for us already, so we know 3x equals 0, x minus 2 equals 0, x plus 1 equals 0. So here we end up with x equals 0. Here is x equals positive 2 and x equals negative 1. This corresponds to the ordered pair of 0, 0. This corresponds to the ordered pair of 2, 0. And this last solution corresponds to the ordered pair of negative 1, 0. Our y-intercepts, or our y-intercepts, since there's only one, it's found by letting x equal to 0. So we have 3 times 0 minus 2 times 0 plus 1. So we have we have 4 terms. 1, 2, 3 of them are non-zero. It does not matter how many of them are non-zero as long as one of these is 0. This whole function equals 0. This corresponds to the ordered pair of 0, 0. Notice this should have been a big hint. If you find an x-intercept at 0, 0, you have just found your y-intercept. You will not have a second one. So if you see this in the future, you can save yourself a little work because now you know your y-intercept. What is the degree of this polynomial? So the degree is found by multiplying 3x times x times x, which is 3x cubed. So the degree is 3. This tells me that we have 3 minus 1, or 2 turning points. So there are at most n minus 1 equals 3 minus 1 equals 2 turning points. Let's look at part B of example 3. What can we conclude about the polynomial represented by the graph to the right? So this is going to go on forever in either direction. Let's call this f of x. Here's our x-axis. Here's our vertical y-axis. What do we see? Well, automatically, or right away, I notice there are 2 x-intercepts. There are 2 x-intercepts. What about the end behavior? If you notice, as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches infinity. So we must have an even degree. Now let's look at these points. 1, 2, 3. I have 3 turning points. There are 3 turning points. So the degree must be at least 4. I think it's reasonable to conclude that this is a 4th degree polynomial. And this concludes section 3.3.